correct?
Yes.
Okay, and you also can see the CC Confer. And now for the CC Confer people, I will share my window. There you go. And I'm taping from my computer. Very good. So before we start, few things that are going on this week. Tonight at midnight, I'm opening midterm number one. So midterm number one covers most of this subject of covers all the subject of um, the scale in the universe, which is pretty much chapter one. Chapter two that deals with night sky and the basic motions that we observe in the night sky, daily or diurnal motion, the yearly progression of stars and constellations in the sky, seasons, and chapter three that has to do with laws of motion. Briefly, I don't explore that a lot in astronomy, although it's very important from the perspective of somebody who is going to study astronomy. But for us, more descriptive astronomy, I don't emphasize a lot. Chapter four is light and telescopes, and those are the main chapters that are going to be asked in this first midterm. So the way it goes, it opens at midnight, and you have about 1 hour to complete, and then so once you open, you have to close, right? If you open and go drink a coffee and talk to your neighbor, when you come back, it's Canvas is going to give you zero. What awfully happened, a couple of students usually get trapped with bad communication or something happened with the computer. And so I opened the exam again, but not the same questions in a couple of days. So Saturday, the exam is going to be open again, and you can try even if you open yesterday, you can try for a second time, and I will collect the highest score of both attempts. So that's how it goes. Um, so I recommend you do anyways. It's always good to do a second time because helps to practice. Okay. So another thing I would like to comment is on the moon observations, the observations that was required. I would change this in the syllabus. The reason is the moon is not in a good um, phase to observe. We have to observe it, early in the morning. It's kind of a funny. So I will pretty much not do it. We do have a visit to the observatory in July, which is the second Friday in July. That's going to be extra credit. It's not required. I had few students online, especially in the summer, commenting they would be traveling, and so they couldn't attend the observatory, and that is a complicated issue. So it's going to be extra credit. If you can make it, great. If you cannot make it, great too. Okay. So those are the main changes in the syllabus. Other than that, are you guys uh, doing fine and getting everything done? I know one of the students was not being able to access one of the extra credits. I don't understand what the problem was. Um, but one of the extra credits was not opening, was requiring or requesting a password, and that was on Astro News. Did you guys had any problem with Astro News?
It's just me.
Let's see if I can find just a moment. This extra credit over here. Astronew, this one. On June 28, 29 is the one that is closing, in fact, tonight. I don't know if you do that one. So you click on it, and then it sends you an article.
Yeah, that's what shows up for me.
It shows?
No, it shows the login.
A login? How? Oh, it's showing to me too.
I can't open it either.
How funny! It's so bizarre because I was able to open, and I send a link to the student. Well, I cancel. Now it's affecting me too. Wait a second. I'm using Safari. Let me try to use Chrome. Modules. So now I'm using Chrome, not Safari. Months phase and Astro News. Here's the link. Interesting. If I do published. Yeah. Yeah, I don't understand. The next big eyes, it gives the opening figure information letter PDF. Click here. Yeah, it doesn't open. Okay, so I have to close that one. Don't worry about it. Poor student, I was saying, hey, what's going on? I just opened, and I open again, and I send the link to the student, and now I can't see it. I don't know what's going on. Okay, sorry about that. I will close that one for sure, but I'm not gonna do it now. So what I would like to go over quickly is star formations and formation of planets, which is the subject of today and yesterday too, chapter 5. So this chapter is very interesting because it sheds some light on how the solar system and planetary systems all over the universe are formed. It's interesting because up to about 20, 30 years ago, we had a theory. In fact, we had a theory called nebular hypothesis for the formation of solar systems since 1800. The basic idea was since Newton had envisioned gravity force as the carrier, the dominant force forming planets and stars, several models came in that would bring in gas that were scattered over a large volume in space, so condense and contract the gas to the point that a star is formed. But in addition to forming a central hot star, because rotation is part of the movement and the motion in the interstellar medium, so as this gas contract, it would also rotate. And as a result of this rotation, the end line of a star formation would be both a star, a central star, and a circumstellar disk, um, pretty much close the equatorial plane of the star. And from this circumstellar disk, planets, comets, the moons would all be come about. So that's the standard model going on since 1800, and several observables in our solar system would support this idea. One, if you look at our solar system, let me see if I can write over here. If you look at our solar system, that's a good one. So you have a central star, and all the planets, they seem to be aligned. If this is a big donut, no, a pancake, better like a pancake. So you place the sun in the center. Of course, this is not in scale. The planets are kind of aligned inside this pancake, like chocolate chips. You like chocolate chips pancakes? It's like that one. So it's all going about that way. So what I'm trying to say, you don't have a planet here, another one down there. So it's all flattened in this pancake-like structure. So obviously, the idea was, well, if you add contraction, if you add like this contraction, but not only contraction, that will lead gas to the central part of this initial cloud, but if you also add rotation like this, if you add rotation, then eventually all this cloud, all this gas will collapse, and you ended up with a circumstellar disk and a central star right in the middle. I mean, this is the basically standard model that we have today, and you observe these ideas not only, and you apply this idea and you support them not only in our solar system but also in other star systems. So that's the idea. So gravity takes a gas that is spread over a few light years and then bring this gas to a central core, and that central core is called protostar. And that protostar, as time goes by, a few million years, as time goes by, this gas contracts and heats up. So the density, which is the ratio between mass and volume, the density of the gas increases, and then the temperature goes up as a result of that. So stars and planets forms as part of the same process. So stars are formed because the gas, as was mentioned here previously, the gas collapse and contract towards the central part. And planets are formed because this disk that is formed as a result of rotation, which appears in here. So the disk that comes out as a result of rotation allows and enables the formation of dust particles and small particles that are called planetesimals. Planetesimals. This is important. So planetesimals are a bunch of junk, of debris that circulate and rotate around the central star, pretty much in the flattened region. Let me show you a movie, since you can see my window. Let me bring about a movie that was very nice. Is EX Lupi UV and video. See if I can find that one. Oops. EX Lupi. Your connection network change. What? EX Lupi. EX Lupi. Why it's not going? The zoom is slowing down everything here. So yeah, this happened last time. Zoom pretty much slowed down my computer and froze it up. Um, of course, Zoom blame my computer. Um, so I can't show that. Hmm. Well, I'm not gonna show. So let's skip with the slides here. I don't know what this is going on here. Hello, can you hear? Can you still hear me? Are you guys still there? Well, I'm taping this, so it's gonna be saved. But let me see if I can now show EXLUPI. Do I lost internet connection? I have internet connection. No, wait a second, this is wrong. Hey, I'm back. It seems that I had some problem with connection. So let me show you, not this one. Can you all see my screen? No.
Yes.
Can you see my screen? All of it?
Yes.
Okay. So I was mentioning about planetesimals and this movie of EXLUPI.
The fading light of a flaring young star
It's interesting because show this phenomenon of star formation. You all can see that, right?
The Hidden Universe Showcase explores exciting new results in infrared astronomy from NASA's Spitzer Space Telescope.
I don't think your
With
screen is
host,
shared right
Dr.
now.
Robert
Can you see my screen?
No.
You cannot? Let me see. Wait a second. Let me go to the Zoom. Share screen. Can you see now?
Yes.
Yes?
Yes.
Like cooking up cometary crystals. You cannot see that, can you? Oh, you can see.
Yeah.
Yeah. Okay. So okay. So let's keep going, and you can hear too. So that's good. So we were talking about planetesimals, and that's how it goes. In this star in
For the most
particular,
part, the universe changes very slowly
uh,
compared to
this star EX Lupi is observable in the southern hemisphere. And what is interesting about it, it's a young star. It's still forming. It's not undergoing any fusion reactions in its core, but it produces bursts of energy, and this radiation, a lot of ultraviolet radiation, creates olivine, which is a mineral that is not so much common in, or we thought was not so much common in circumstellar disks, but it can be found in magma chambers. But see how interesting this is. So you have this circumstellar disk, and at a certain distance from the star, the stellar magnetic fields disrupt, and then the disk itself doesn't reach the star. But you can see all these granules, all this dust. They are in fact crystals that will grow in size, becoming what we call planetesimals. And these planetesimals will collide, will grow in size, and eventually form um, the objects one of it we are living in: planets, moons, satellites, comets, and asteroids. And so all these chunks that you can see right here, they are called planetesimals. And the disk all rotates, as you saw previously in this shot right here. So the disk all goes in the same direction. And that's why it explains why our all planets in our solar system, they rotate around the sun, all going in the same direction. And with rare exceptions, the planets themselves spin in the same direction, because that's the original direction the cloud itself, the circumstellar disk itself, was rotating. Um, it's this is it goes in a little bit of physics and spectroscopy that I don't want to call your attention to it now. But the main point is to show how this circumstellar disk gives rise to dust, and then to granules, and then to bigger particles, and eventually they grow in size, and they become, planets. So now you can see this star forming protostar. Can you see this slide over here? And I wrote planetesimal right there. You can see it? Okay, we are all good. So eventually, this circumstellar disk gives rise to a central star right there. See that? And outside, you still have a lot of material that eventually will coalesce and form, bigger objects. So as the star heats up, now the star irradiates heat, which means in the regions close to the star, you shouldn't expect to find a lot of ices, right? You should expect to find ices in regions further out, in the outskirts of this disk. But in the regions close to the star, you can find minerals and crystals that are nicely formed at a higher temperature. So when you form stars, because of the temperature, because of the heat coming out of the star, so if this is a star, in the region exactly close to the star, you tend to form a type of planet called terrestrials, or planets that happen to be more rocky type. As opposed to when you probe regions further out, you form planets that are more Jupiter-like. And what recent investigations on planet formation indicate that sometimes these big planets formed in regions further out, they migrate and they might end up mixing with terrestrial planets. But in a classical sense, you would expect to find rocky type planets closer to the star and more volatile and lighter or less dense types of objects and icy type in regions further out. This is another display showing the same idea, a central star, disk rotating, and the star heating up, and out of the disk, crystals or minerals formed in high temperature can come about. Now, eventually, stars will achieve high temperature, and the ball game is 10 million Kelvin. We'll reach this high temperature in the very core, in the central part, which is indicated in these pictures right there. And when this temperature is reached and when the density is high enough, fusion reactions will take place. So these fusion reactions is what convert hydrogen atoms into helium atoms and energy. So basically, fusion reactions correspond, in the case of the sun, 4 atoms of hydrogen will fuse in the very core because of this high temperature and pressure, producing 1 atom of helium plus energy. And this energy is what will keep the star stable, preventing the star itself to continue its collapse to a black hole, if you will, right? So this energy produced in the very core is released and help to balance the star somehow. So I have this classic question. As the protostar collapses, its density increases. The temperature also increases. And the brightness also increases. Everything increases. Of course, the size diminishes, right? Becomes smaller because it condensed. Now you have more pictures. That's a nice picture of a circumstellar disk we are seeing edge on, and this bipolar flow that comes out of this newly formed star. Another picture of a star forming region. Hey Thomas, do you have a question? Thomas? I assume Thomas is anybody? No one is in the CC Confer. Hello? Hello? Hello?
I'm still here.
Oh, okay. Okay, so let me go back to here. Now, this picture here indicates what I was mentioning before. So you have a central star formed somewhere here, and this is the circumstellar disk going around the inner part of the disk, and where Jupiter, Saturn, and Uranus would be located. But these planets, they are called the terrestrial planets, Venus, Earth, Mars. They are rocky type because of the heat and the solar wind that originates in the sun itself. And since they are too close, and the environment and the density in this region is such that you cannot form ices. So there is no point of forming ices in that region. But you do form rocky type material, and there is a very nice region called habitable zone that you might harbor planets with water. So the temperature is just right for water to be formed, and astronomers nowadays they look for this habitable zone as a as a as a possible region around the star where life could develop, could pretty much grow. So atmosphere. So when you think about atmosphere in planets, especially terrestrial planets, so there is a primary atmosphere which in general is associated with hydrogen and helium, because those are the most abundant atoms in the universe. So 75% of the universe is hydrogen. You have basically 25% of helium, and the rest is just trace amounts. So when the rocky type planets are formed, so they are surrounded by a thin atmosphere of hydrogen and helium who goes away because of the solar wind. So the second atmosphere that comes about is pretty much the one formed by volcanoes. When the surface, the planet's surface, start cooling down and crystallizing like it happened here on Earth, then volcanoes are naturally formed, and gases, primarily carbon dioxide, perhaps some nitrogen, and sulfur coming out of these volcanoes. So the secondary atmosphere, and this is true not only for Earth but for Venus and Mars. The secondary atmosphere was primarily carbon dioxide. Now, carbon dioxide reacts with water. So planets in the habitable zone like Earth, it got to a point in its history where water could be formed, and this water rain down and reacts with the atmosphere, carbon dioxide forming carbonic acid, and all of that washed down to the oceans. So the carbon now in the oceans is being used as primary element to be part of the cells and bodies of the living organisms information. And eventually these living organism information die out, their bodies sink down to the bottom of the ocean, and now we call that limestone. So the Rocky Mountains are primarily little dead organisms that were the first one to make use of this carbon dioxide. It's a cool one. So when life kicked in on Earth, some organisms start to produce oxygen, in fact, to release oxygen in their search for energy. And then other organisms develop the ability of using oxygen to produce energy, to produce sugar. So we are one of those organisms. We need oxygen. So oxygen, first produced by these bacteria, they were incorporated into existing rocks. And geologists can time down exactly the moment in Earth history where these rocks were formed. And eventually there was a surplus of oxygen in the atmosphere that raises up to form the ozone protective layer in the troposphere, and eventually life grew to be complex and large, and and here we are. So oxygen is a telltale of life, for sure, but other gases are also indicative of life activity, and probably in the next few years, once James Webb Telescope is launched, astronomers will start suggesting life in exoplanets as they observe and detect certain molecules, certain gases in their atmosphere. So this chapter is interesting because it explains how not only stars are formed, but also how planets are formed and why we have this difference in planets in our solar system. Okay. And that was all she wrote. Do you guys have any questions you would like to ask? So I have Tan Nguyen, Rishi Parikh, and I have Anne Nguyen, and I have Thomas. Any question you guys want to ask? So I hope it works, but I'm not gonna use the Zoom.us anymore. It's the last time. So next week, let's go to ccconfer.org. Would be nice to try. Yeah. See, that's the problem with Zoom. In the middle of the meeting, it just cancel. But I'm taping. So it's gonna be in ccconfer, and hope see some of you there.